Okay, so the first thing for Wallace's formula, he says, is to use integration by parts on this. So we let, it's a UdV, so we let u equals sine theta plus 1 and dv equal to sine x dx. That way...
Keep that over when we get to your right. Okay, that's good. Oh, that's good right there.
Okay. Okay, so when you do that, you have your u v, so negative cosine times the minus the integral of there's a v again and then du. So this is just 0. Cosine of or the sine of pi and sine of 0.
Pi.
So then you have the negatives become positive, so you have n plus 1 sine n cosine squared, which you then write as 1 minus sine squared. Then you split up the integral. So you have the sine to the n minus the sine to the n plus 2. Okay? And then you move this back over. So you have n plus 1 plus 1 sine. So you have n plus 2.
Oh, okay. It's that.
It's one of those ones where you move it back to the other side.
Okay. Yeah.
Okay?
Yeah.
So that's how you get n plus 1 over n plus 2.
Okay. Yeah.
Okay? All right. So then, now here's the reasoning that I was thinking of. He just puts this inequality there, and I had this sort of reasoning. Since sine is between 0 and 1, higher fractional or higher powers are going to get smaller, not fractional powers. Fractional is not supposed to be in there. Right, so I was thinking like, because it's between 0 and 1, like sine squared would be less than sine to the first, which would be less than sine.
Perfectly with it.
Okay, so then what you do is you divide this inequality by the right side.
Well, the only thing we have to worry about is the sign always being positive at the interval integration, but it is.
Right, yeah, it's between 0 and pi. Okay, so we divide by the right-hand side of the inequality, which gives you this.
Okay.
Yeah, because the right-hand side cancels out. Okay, so then the next thing we do is simplify this sine to the 2n plus 2 using the formula that we just proved, this one up here. So we just plug in 2n. So we just get 2n plus 1. Okay. So then the inequality becomes this. So the 2n plus 1 over 2n plus 2, that's just from the formula. You can bring sine to the 2n plus 2 down to sine to the 2n. And the reason he does that is so these cancel. We had this inequality right here, and then he uses this formula right here, just replacing n with 2n.
Oh, then I have sine 2n plus 2. It's 2n plus 1 over 2n plus 2 sine 2n.
Right here.
Okay, got it.
Yeah, so then you have your 2n plus 1 over 2n plus 2
Right.
up in the numerator, and all this garbage is going to cancel.
Okay.
So you're just left with, now you have only the 2n plus 1 over 2n plus 2. Good stuff? Okay. Now he plays around with these two things. First we show that the integral of sine to the 2n is that, and we do that by induction. So when n is 1, we're doing the integral of sine squared, which I just did that for our case. 1/2 minus 1/2 cosine 2x. So then when n is 1, the formula should give pi over 2, which it does. So then we assume, and we would like to assume it's true, and I guess I should be using a different index like k, but that always confuses me when I'm doing this. So then you replace n everywhere with 2n plus, or excuse me, you replace n with n plus 1, so you get 2n plus 2. So then it just tacks on one more term, right? So we want to show that this is equal to this.
Yeah, there's a question mark over that equal
Yes.
Well, you know,
Exactly. But we've done the hard part already because we have that formula we can use.
oh, yeah.
So we use this. Sine to the 2n plus 2, we can bring it down to, and we have that. And we use the inductive hypothesis, because we already know what that is. It's that. And this is just the term that we need. So that works out beautifully.
Okay.
So I actually have the proof.
That's beautiful.
Yeah, the next one is just pretty much the exact same thing. We're now showing we're looking at this inequality, and we've simplified this one, and now we just work on this one. So we show that sine to the 2n plus 1 is that, 2 times 2/3. So n equals 1 is sine cubed, 1 minus sine squared, times the integral, and it's 4/5 from calc 2, right? I don't need one. So then when n is 1 in the formula, we have 2 times 2/3, which is 4/3. So that works. So now we assume that it's true, and we want to show for n plus 1. So then we have 2n plus 3 is equal to, so if you put n plus 1, you're going to get 2n plus 2 over 2n plus 3. And the exact same thing happens. You replace n, but the hard part is I had to realize you replace n with 2n plus 1 in the original formula. So you have 2n plus 3 down to 2n plus 1. But that wasn't bad. So you replace, so there's the inductive hypothesis, and then you just move this back over. So there, we have it by induction. Okay, so the original inequality was this. And then using the formulas we've proven, which are at page 30, we have this, right? Those multiplication formulas. So what I did here was you have the 2 over pi, and then I think I kind of flipped everything.
Yeah, the 1/2 goes up.
Right.
The 4/3 goes up.
I wanted it to start looking like the answer, what we're going for.
Yeah.
So if you multiply by pi over 2 on both sides, I think what he was trying to go for was like the squeeze theorem. So you would have multiply both sides by pi over 2, and you take the limit as n goes to infinity. Does that sound reasonable? So then you end up with pi over 2 is less than or equal to this, which is less than or equal to pi over 2.
Yeah.
So it proves that pi over 2 is equal to that.
Beautiful. Is Buzz Wallace have the squeeze theorem? Is this how Wallace did it?
That's a good thing to look up. Because he was talking about taking limits in the text. He says shows that as it goes to infinity.
Oh, that's beautiful.
Yeah, it was really cool. It was really nice to.
I was glad I could do it.
Oh yeah.
Can you give me that electronically?
Sure.
And I'll stick it on the web.
Yeah, I have it in my email.
Good.
Yeah.
What are you using for your?
I use math type. It's really
Is it on that like 5?
I think there's 6 now. I don't know. But I'm still using like 4 or something. I've had it for so long.
Yeah, I always use sign for that's very nice. It's pretty.
Yeah, it is.
That was a very good explanation.
Thanks.
It's a calc 2.
I was wondering. Yeah, it's
It's a calc 2 program, but
It is.
that's way beyond. If you showed that in calc 2 class,
they cry. It's yeah.
hypnotized.
Yeah.
That's good. And who was Wallace anyway?
That's a very good question.
Was he before or after? So he was a rough contemporary with John Wallace. What did he do? Is he the one that invented the symbol for time? Ratio circumference to diameter. Was he the guy that did that? They usually attribute all that stuff to Euler, but I don't think Euler actually did all that. Is it Wallace that started using pi for the ratio? With math history people, I have.
No, I don't think so. I don't remember studying Wallace at all.
Just because
No.
remember Wallace as being the inventor of the notation for pi, but then I might have that backwards, or not at all. It's from that era. Okay. A few preliminaries here. So,